We live in a remarkable time. Humanity has walked on the moon. We've sent robotic explorers to the distant shores of Mars, Jupiter, and even beyond the edge of our solar system. For over 60 years, we've relied on one fundamental principle to achieve these incredible feats. This principle is the rocket. It's powerful, it's brilliant, it's a testament to our ingenuity. We burn fuel, throw mass out of the back at great speed, and push ourselves in the opposite direction. It's Newton's third law, in its most dramatic form. This method has served us well, opening up the heavens and transforming our understanding of the universe. But what if this is just the beginning? What if the rocket, the very symbol of the space age, is also its biggest limitation? Rockets are like trying to cross an ocean in a boat that must carry all of its own fuel, and the fuel for the fuel, and the fuel for that fuel. The problem with rockets can be summed up in a simple, yet ruthless piece of mathematics. It's called the Tsiolkovsky rocket equation. You don't need to know the maths itself, but you need to understand its profound consequences. Think about it this way. For a typical rocket, something like 90% of its initial launch mass is just propellant. Only a tiny fraction, maybe 3 or 4%, is the actual payload. That's the satellite, the telescope, or the capsule carrying the astronauts. This makes deep space exploration incredibly expensive and difficult. Every gram matters. Every instrument, every solar panel, every scientific sensor has to fight for its place on a vehicle that is almost entirely fuel. It is an unforgiving law of physics. This tyranny of the rocket equation, as it's often called, has shaped the entire history of space exploration. The Voyager probes, which have now left our solar system, took decades to reach their current positions. The future of space travel will not be defined by a single solution. Instead, it'll be defined by a diverse new toolkit with different tools for different jobs. Getting off a planet's surface is one challenge, while traveling between planets is another. And voyaging to another star is a challenge of an entirely different magnitude. For each of these tasks, engineers and physicists are developing new and exciting concepts. These are not just ideas from science fiction, they're based on solid scientific principles. The first set of tools in our new kit are tethers and slingshots. These are wonderfully elegant ideas that use the principles of orbital mechanics and gravity to their advantage. Imagine a spinning weight on the end of a string. If you let go at the right moment, the weight flies off at high speed. A space tether works in a similar way. The second set of tools involves propulsion from a distance. This is where things get really exciting. This is the idea of beamed energy propulsion. Let's begin with one of the most elegant ideas in our new cosmic toolkit. It's the space tether. The concept is wonderfully simple, almost like something a child might dream up. Imagine you have a very, very long and incredibly strong piece of string. Now imagine you're in orbit around the Earth, holding one end of this string. At the other end is a satellite or perhaps a small cargo pod. This isn't just any string, it's a high-tech cable, possibly made from materials like carbon nanotubes, designed to withstand the immense forces of space. What makes a tether so special? It's not just a passive rope. As this long cable orbits the Earth, it interacts with our planet's gravity and magnetic field in fascinating ways. Because the tether is so long, sometimes many kilometers, the top end is orbiting slightly slower than it should for its altitude, while the bottom end is orbiting slightly faster. This creates a constant tension along the cable. This tension is a form of stored energy. The real magic happens when you use this stored energy. By timing things perfectly, you could release a payload from the top end of a rotating tether. This would fling the payload into a higher orbit, or even send it on a trajectory towards the Moon or Mars. So, how exactly does a tether fling a spacecraft across the solar system? The most captivating version of this idea is called a rotating skyhook. Picture a long tether spinning end over end like a propeller, all while it orbits the Earth. Imagine a spacecraft launching from Earth on a relatively small, cheap rocket. At that precise moment, the lower, slower-moving tip of the rotating skyhook swoops down to meet it. The skyhook carries it upward and forward, accelerating it dramatically as it rotates. After being carried through half a rotation, the spacecraft reaches the highest point of the skyhook's spin. With another precisely timed maneuver, the spacecraft detaches from the tether. It is now flung away at this new, higher velocity. Beyond the clever mechanics of tethers, there is another technique we can use to navigate the solar system. We call it the gravity assist, or more informally, a slingshot. Imagine playing a game of cosmic billiards where the planets are giant, moving balls. The principle is surprisingly straightforward. When a spacecraft flies close to a massive body like a planet, it enters its gravitational field. The planet's gravity pulls on the spacecraft, bending its path and changing its speed. The planet is so massive that it doesn't even notice the loss. It's like a fly bouncing off the windscreen of a speeding lorry. The fly's trajectory is changed dramatically, while the lorry's speed is altered by an amount so small it is impossible to measure. Perhaps the most spectacular use of the gravity assist technique was a mission that took advantage of a rare celestial alignment. In the late 1970s, the 4 giant outer planets were all lined up in a special way. This was an arrangement that only happens once every 176 years. This ambitious plan led to the creation of one of the most successful exploration missions in history, the twin Voyager spacecraft. Launched in 1977, Voyager 2 was sent on the full Grand Tour trajectory. Voyager 2 flew past Jupiter in 1979, which propelled it towards Saturn for a 1981 encounter. The slingshot from Saturn then sent it on its way to Uranus, which it reached in 1986. Finally, the gravity of Uranus aimed it towards its final planetary target, Neptune, which it flew past in 1989. For all their power and elegance, gravity assists are not a perfect solution. The most obvious drawback is timing. The planets have to be in the right place at the right time. If you miss your launch window for a complex multi-planet tour, you might have to wait years, decades, or even centuries for the next opportunity. Another major limitation is that gravity assists make journeys longer in terms of time, even as they save fuel. While this is acceptable for robotic explorers, it presents a serious problem for human spaceflight. So, we've explored the clever mechanics of tethers and the gravitational dance of slingshots. To take the next great leap, to travel faster and farther than ever before, we need a more active approach. This is the revolutionary idea behind beamed energy propulsion. The fundamental principle is actually surprisingly simple. Light, although it has no mass, has momentum. When a photon, a particle of light, bounces off a surface, it gives that surface a tiny push. But if you could fire an incredibly powerful, focused beam of light at a very large, very lightweight, and very reflective mirror in space, the combined push from trillions upon trillions of photons could be significant. This brings us to one of the most audacious and inspiring projects ever conceived. It is called Breakthrough Starshot. Its goal is nothing less than to send the first human-made probes to another star system. The target is Proxima Centauri, the closest star to our Sun, located just over 4 light-years away. The probes themselves, called starships, would be marvels of miniaturization. Each one would be a complete spacecraft, with cameras, sensors, and communication equipment, all packed onto a wafer no bigger than a postage stamp, and weighing only a few grams. The engine for this mission would be a colossal laser system on Earth, possibly covering several square kilometers. This light beamer would combine the power of many individual lasers into a single incredibly intense beam of up to 100 gigawatts. For a few minutes, this beam would be focused onto the sail of a starship that has been released into orbit. The sheer pressure of this beam of light would accelerate the tiny craft from 0 to 20% of the speed of light, that's 60,000 kilometers per second, in the time it takes to make a cup of tea. After this initial push, the probe would coast through the darkness of interstellar space for 2 decades. Upon arriving at Proxima Centauri, the nanocraft would fly through the system, snapping pictures of its planets and collecting data. This information would then be sent back to Earth using a small onboard laser, a journey that would take another 4 years at the speed of light. But Breakthrough Starshot is not science fiction. It is a serious engineering project backed by leading scientists and entrepreneurs. The future of space travel won't be a case of one technology winning out over the others. Rather, it will be about building a sophisticated, multi-layered transportation system where each tool is used for the task it does best. For routine traffic in the Earth-Moon system, Tethers would be the undisputed champion. Imagine launching a cargo pod on a small, reusable suborbital rocket that just has to reach the edge of the atmosphere. There, the lower tip of a rotating skyhook swoops down to grab it. For robotic exploration of the outer solar system, gravity assists will likely remain a valuable tool for a long time. When time is not the most critical factor, using a slingshot from Jupiter is still a brilliantly efficient way to send a heavy scientific probe to Saturn or beyond. For the most demanding journeys, fast human missions to Mars or robotic probes to the stars, beamed propulsion is the only real contender. A human crew heading to Mars could have their ship accelerated by a powerful laser for the first part of the journey, drastically cutting their exposure to deep space radiation. In this grand system, each technology solves a different piece of the puzzle, creating a network that is robust, flexible, and incredibly capable. They promise a future where travel around the solar system becomes routine and affordable, and where the journeys to other stars are measured in years, not millennia. We find ourselves at a remarkable crossroads in our journey as a species. For millennia, we looked up at the points of light in the night sky and wondered what they were. For the last 60 years, we've taken our first tentative steps into that vast darkness, powered by the controlled explosions of chemical rockets. We've walked on the moon and sent our robotic eyes and hands to worlds our ancestors could only dream of. But we've reached the end of what brute force alone can achieve. The rocket has taken us to the shore of the cosmic ocean, but to truly set sail, we must learn to be sailors, not just passengers on a fiery projectile. The ideas we've explored, tethers, slingshots, and beams, represent a profound shift in our relationship with the universe. They are a move away from fighting the cosmos to working with it. Tethers and skyhooks ask us to dance with orbital mechanics, exchanging momentum with grace and efficiency. It's the beginning of a future where we are not just visitors in space, but true inhabitants. A future where travel between planets is routine and affordable could lead to a multi-planetary civilization, safeguarding the future of humanity. A future where we can send probes to other stars is a future where we can begin to answer one of the oldest and most profound questions we have ever asked. Are we alone? The journey towards this new era of space travel will happen in stages. We're already seeing the first steps. The successful flights of solar sails like Icaros and LightSail are proving the principles of sail technology. In the coming decades, we can expect to see these technologies mature. Each small success will build upon the last, slowly but surely constructing the infrastructure for a new age. These grand projects will require cooperation and a shared sense of purpose on a global scale. The stars are not our destination for tomorrow, or even the day after, but they are our ultimate destiny. The universe is vast and full of wonders, and it's waiting. We're learning how to write our own story among the stars, a story of a species that looked up from its small blue world, dreamed of what was possible, and then had the courage and the ingenuity to go out and achieve it. The journey will be long, but it has already begun.